Hello, people. We can start the discussion. First of all, I would like to answer questions about the simulation that were submitted, and then we will go forward with the theoretical questions or uh, calculations. I will share my screen to show you the question and to explain a bit my answers. Okay, I hope it's visible now. Is it visible?
Sim, professor. Tá
Okay,
sim.
very nice. So the question of Mateus, that simulation goes well, right, for inviscid flow, and convergence happens. This is the flow picture, quite nice. Normal shockwave appears. For the viscous simulation, it's a bit different picture, right? We have a boundary layer quite visible here, and I think quite thick boundary layer, but okay. And then we have a normal shockwave, and in this region, flow separation. Because of presence of the shockwave, we start to have flow separation. What happens here in this region, if you visualize the streamlines, you will see that there are vortexes. Flow is going not just in one direction to the exit, but also goes in the opposite direction near the wall and creating such a vortex. So flow has low velocity. Flow is definitely subsonic here in this region and interacts in some way with supersonic flow before the shockwave and subsonic compressible flow after the shockwave. It's usually characterized by very unstable flow behavior, since we also involve the viscous model, and physically this flow cannot converge, not just mathematically, but also physically. So such a picture that is shown here about the convergence we can consider as already converged flow, finished flow. Okay, so don't worry if you receive such a result. This is quite normal when the big flow separation region appears in this transition from supersonic to subsonic in the boundary layer. It's very, very typical convergence picture. So you can consider if you reach the flow structure same or very similar to the inviscid flow structure, like you can see here, all the shockwaves already established, you can stop your simulation. You do not need to wait more than 20,000 iterations. Also, what can happen in this case is that your flow has a vortex, right? And the flow is more constrained, so the efficient flow passage here is smaller than you had for inviscid simulation. So flow must have higher values of pressure, for example, density, and probably will have a bit higher values of temperature. And in this case, you may start to observe that the shockwave is starting to go outside of the diffuser. You do not need to wait until it's destroying all the flow. You just finish the simulation at this point when it has same configuration as this shockwave structure for inviscid flow, and you finish. You just stop simulation. It will never converge, as it will be never converged, as may be seen from here. What we can see here that was established, the knot is characteristic of the turbulence model, so probably you have used here Spallert-Almares turbulence model, right? And already has 10 minus 4, so the viscosity in the boundary layer already has been established, and the change is very low from one step to another. It means that your boundary layer is already has been formed in this simulation and will not evolve anymore. So you finish at this simulation at this point when you reach this flow structure and produce the final report. We go to the second question. It was also a question of Mateus about the simulation of the nozzle, right? The simulation of the viscous flow in the nozzle. We can observe the boundary layer formed here, very thin boundary layer, And also we may see this flow behavior. It looks like a shockwave. Looks like a shockwave, very weak oblique shockwave when flow transits from one region to another. This happens when our nozzle is not isentropic, because you had not, and I did not design this nozzle to work in isentropic conditions. As you already know from the theory, the isentropic nozzle must be created with some specific method, like method of characteristics. And here in this calculation, method of characteristics has not been used, and flow is not isentropic completely. So we have this shock wave inside the nozzle, and it's quite normal for such flow structure. It's expected to have such a flow structure. It is not a problem. It's not a problem from the computational point of view. It's the problem from the optimal flow, of course, because the nozzle is not isentropic and the losses will happen. But from the point of view of your calculation, there is absolutely no error. Flow is expected to be like this, and if you will start to optimize the supersonic shape here, you can decrease this region of low velocity. You can decrease the strength of the shock wave in this region. It means decrease the drop of the velocity here and rise of pressure. And you can improve the characteristics of the efficiency, like stagnation pressure ratio. And it's possible to do this kind of optimization if you want, if you would like to do. I ask it. It's not obligatory to make this optimization, but if you like to do it, or you have enough time to do it, you can improve the shape of the nozzle to reduce this zone. What is not obligatory task for work to. Okay, residuals that we are expecting here, they will be probably like this, or they will be also, they could converge to some value, like usually we have convergence until 10 minus 3, 10 minus 4, and we stop the simulation, right? And depending on the model you are using, depending on the geometry you are using, convergence can be like this, or convergence can be for all parameters, not just for the K and omega, for K omega turbulence model. In this case here, these disturbances, they happen when we are simulating our boundary layer. Probably there is some uncertainty because model is changing, type of the model, type of the equation system is changing when flow transits from supersonic to subsonic region, and this mathematical oscillation happens. It's quite visible that it's just some mathematical problem here. It's absolutely no physical problem here. K and omega parameters, they converge faster because the physics of the model, right? The viscosity, they have some dissipation member in the equation, and because of the dissipation, these oscillations, mathematical oscillations for turbulence model, they are dissipated, they are reduced from one step to another. It's the process. Probably here in this calculation you have also used high order of simulation. Maybe it was second or third order. Just let me know which, first order and second order also does not converge. So it means that transition. Problem is transition. Problem is not the method of solution. Transition from supersonic to subsonic region, I mean, is also not a big problem if you have a good convergence with analytical data you calculated in work 1. It means that you reach the good results. You will have some difference with respect to work 1 in the region of the exit of the nozzle, because this shock wave here was not calculated analytically, right? And since there is no such calculation, at the exit points of the nozzle, you will have a bigger error with respect to the work one. Okay, in all other points in the throat, in the inlet section, should be very, very good correspondence until this moment appears, which has not been calculated in work one.
Se eu puder tirar mais uma dúvida
Please ask.
Sobre essa tubeira mesmo, hoje eu tentei simular a tubeira cônica e quando eu fui simular para o caso viscoso também, ela convergiu. Então, tipo, pode ter essa divergência, né, por conta, que nem você falou, do parâmetro geométrico dessa tubeira, né?
Yes.
Entendi. Aí eu acho que eu falei também, mas, por exemplo, o valor na saída não deu muito diferente. Tipo, teve um erro na segunda casa decimal, algo assim, do valor analítico que eu calculei, né? Se pegar o parâmetro de area weighted average. Então, posso dar como ok, né?
Yeah, please do not forget to use area weighted average, because area Mach number relations you used in work one, they are giving average values. So in the simulation, you also need to have average values of the flow, not flow properties on the wall or on the axis. It should be average, taken by the area average tool in the Ansys Fluent, or using the console command which I showed in the video to take the average along the axis. Both of these operations, they are equivalent, and you can use one or the other. But you know which is better for you, you choose and you use. Convergence of the flow is depending on many, many factors, including the shape. If you changed your shape, of course, convergence can change. Not obligatory, but in some way it will be improved, the convergence, or will be worse. Okay, I would like to answer the third question, is about the simulation of the nozzle from Lara. And here she said that flow is converged with respect to the theoretical results, right? And for my opinion, this Mach distribution is okay. It's not a problem. Just in the part of the inlet, this point on the left upper angle of the nozzle, it has a very small values. It happens, I think, because flow is rotated, right? Flow is horizontal. You gave a horizontal inclination initial of the flow, and here is not compatible with the wall because it's inclinated. So flow must rapidly change its direction, and it means that it will decelerate with respect to all other points. So this deceleration happens because your flow is horizontal before, and then it changed rapidly the direction. Is normal, but always can be improved if you define not the uniform distribution of the velocity, but the distribution of the angle from zero on the axis until the velocity direction on the wall same as the wall direction. But it's absolutely not an issue, not a problem for simulation, which I asked you to do in gas dynamics. So you can deliver as it is right now, and it's quite good. We can see the sonic line here is the line where the Mach number has value equal to 1. Is quite expected, this shape, as well as the supersonic flow distribution, quite low supersonic Mach number, maximum 166 in the nozzle. And it's also good. So this simulation can be accepted, and as you say, it's converges with analytical results. Absolutely will be not a problem to be evaluated and to be compared with analytical solutions. So keep working in this way, just missing the viscous part, right? I would like to go to our tasks of gas dynamics. Today we will discuss 2 questions. I would like to finish giving these explanations today. It's about item 5, isentropic flow relation, when the flow goes according to the isentropic functions, right? There are no losses, so what we have basically is constant values of stagnation pressure and stagnation temperature, and also stagnation density because of this. The efficiency is 100%, so stagnation pressure does not change. And we have a simple formulas. Probably it's one of the simplest questions to solve these parameters. We have just one example here. Like we have defined flow properties at point A. They are static, stagnation, some properties, right? And we have to calculate the flow properties at the point B, static or stagnation properties. To make this calculation, we are using the basically different forms of the energy equation, and we apply these forms of the energy equation for our thermodynamic or flow properties. Let's make some examples, and we can close this question quite easily. I will show you that equation system, right, or equation model, and these results are from the chapter 8 already. So we are talking about special forms of the energy equation. They give us the relation between temperature and velocity in different point. They are giving relation between speed of sound and velocity in 2 different points, including the stagnation point. Also, they are giving to us relation on thermodynamic properties to Mach number, like this: pressure, density, temperature initially, and these equations, of course, with use of the of this formula 841, and the relation on the characteristic point where Mach number is equal to 1. Okay, characteristic Mach number relation to the real Mach number relation, and vice versa, calculation based on real Mach number of the characteristic Mach number. So these are basically all the equations you need to know, to remember that they exist to solve the tasks on isentropic flow. So let's go back again to tasks, and let's have the example 5.1. Okay, let's define some flow properties. Very simple. At point A, for example, we have the speed of sound 300 meters per second. At point A, we have the velocity at point A, okay, 100 meters per second. And at point B, we can define any other flow property. For example, that it's 200 meters per second. Right, at point 2, and A2 speed of sound at point 2 is unknown. Is the task basically equivalent to the definition of temperature, but here just in terms of the speed of sound. Relation between temperature and speed of sound, I will remember you, it's square root of gamma RT. We go to the equation. In this case is the equation 836, right? 836, and here is given the flow properties are given. So from this equation 836, we can express what is the speed of sound. What we do, we put to the left velocity in square divided by 2, and then we multiply all by gamma minus 1 and take a square root. So I will take here, and I will write that A2 would be my square root 1 divided, multiplied gamma minus 1, right? And inside the brackets we will have A1 gamma minus 1 plus velocity 1 divided by 2 in square. The speed of sound is also in square, and minus velocity 2 in square divided by 2, like this, and the square root from this function. It's quite simple to solve, right?
Professor,
Yeah.
tá cortando um pouco depois da raiz.
Yeah, sorry. I will try to move and to make it smaller. Okay. Sorry, I did not see that it's not visible because it's in a part of my screen as well. Okay, I think this is the correct expression. And here is just to substitute the values. We need to substitute the speed of sound. We need to substitute the velocity before, so velocity after here, and gamma. Gamma is, as known, is 1.4 for the air, so it's quite simple to calculate. So this task can be given for you to be solved, and it's simple. I will not find here the final solution, right? But I think it's quite clear for you that just to put the values here and to calculate. Take care, it will be also can be some trick. Here, if I say that the velocity will be very high, for example, can be negative, right? Bigger than this part of the positive side of the equation and can be negative under square root. So this velocity will be not possible to achieve by flow acceleration because flow is inside, as you remember, is inside the potential energy. So if we spend all the potential energy, which is the temperature basically, temperature drops so much that acceleration will not be possible anymore. But I hope I will not give you such, I think probably I will not give you such a question where you will receive a negative root from the function. Same way you can solve not from point A to point B, from point 1 to point 2, but from point B to point A is absolutely reversible operation, right? And you can do it in any direction. Another task we can have, okay, it was, let's have example with the temperature. For example, I have temperature 1 is, okay, let's see, temperature, flow is decelerating. Temperature 1 is 300 Kelvin, temperature 2 is 400 Kelvin. Okay, and I know what is Mach number 2, for example, or should it be okay? Mach number 2, we can define any value, can be supersonic value, subsonic. And in this case, okay, let's take one subsonic value. We are working in isentropic region, right? So 0.5. And we are interested to know what is Mach 1 at point 1 or at point A in this case. To find in a solution in such a way, we need to use our isentropic relation. We go back to the equation 840. Right, this is the relation between temperature and Mach number. And here we will just write that temperature 0 is constant, no matter which is the point. So I will write that temperature, okay, from this equation, temperature 0 by temperature 1, temperature 2 is a function of Mach number 2. This I will not calculate here, I will just take from Appendix A from the book, and I will go there. Just will note here which is the page number, is page 567. Nice. So go into Appendix A and try to find my Mach 5, my Mach 0.5. This is it. And going to the temperature ratio is 105. 105 is should be a positive value because stagnation, and more than 1 because stagnation temperature is always bigger than the static temperature. 105. So then I will use the left side or the first point of my flow, point 1, and I will write that T0 by temperature 1 is some function, but for me is not important. Now it's already calculated as temperature 2 multiplied by 105 and divided by temperature 1. Okay, this is it. I just need to calculate how much is that. It's 400 multiply 105 and divided by 300 of T1. So it's 1.4. 1.4 is some function of Mach number 1. From here, I define my Mach 1 from appendix. Okay, I'm looking where is 1.4. Approximately is closest point is this one, 1.4, and I see that my Mach number is 142. So my Mach 1 is 142. Okay, this is it. If you would like, if I will ask you to calculate not just Mach number, but for example, calculate which is the value of the velocity, you can also do this. Just use definition of the Mach and the speed of sound, and the velocity 1 will be found as Mach 1 multiplied by square root of gamma RT1. Okay, I will not calculate right here because I think it's quite obvious. We already take the values known. T1 is known, R is gas constant, gamma 1.4, and M1 is Mach defined. Right, Mach just found 142. Do not forget the gas constant. It should not be universal, but the constant for the gas, which is equal for air as 8314 divided by 29 molecular weight of the air, average molecular weight. And with this value, you are okay calculating the flow properties. Okay. Let's have another example, probably. So we had previously temperature 1, temperature 2, we had Mach. And now let's go to, for example, other parameter like pressure. I would like to see that, for example, my pressure at point 1 is 1 atm and my Mach number of the flow is 2, and flow is decelerating in, for example, isentropic diffuser, and it was decelerated until Mach number 0.5. I would like to know which is pressure at this point. And here I also use my isentropic relation. First of all, define P0, right? Similar to the previous task. I just will find my Mach 2 in isentropic table, isentropic flow properties table. Let's see, Mach 2, okay, this one, and the pressure ratio is this one, is 7.824. So P0 is 7.824 corresponding to Mach 2, and I multiply by 1 atm of my pressure 1, and will be equal exactly 7.824 atm. Now to calculate P2 is quite simple. I just go to see my Mach number 0.5. This is my Mach number 0.5. I see again the pressure ratio is 186. So I will see that my pressure 0 divided by pressure 2 is function of Mach number 2 and equal to 1186, right? Since my pressure 0 is already defined, I can use it for the calculation, and then my pressure 2 would be simply calculated as a ratio P0 divided by function of Mach number 2. Yeah, should divide, not multiply, because the static pressure is always smaller than the stagnation pressure, same as temperature, same as density, right? And we are dividing by the value smaller than 1, so the result will be smaller than the P0. 7824 divided by 1186. Let's see. 6.6 approximately. Okay, this is how you calculate pressure 2. That's it. Maybe in some task will be given not just pressure but also the density. And I will ask you, please calculate the Mach number or calculate the speed of sound. If the density is given, you can calculate temperature by the equation of state. You remember, right? That pressure is equal to density gas constant temperature. From this, if two parameters here are given, the third parameter can be easily calculated. From here, temperature can be obtained as pressure divided by rho r, okay, and the speed of sound. Actually, I like a lot this equation of speed of sound. It's so nice, just 3 letters under the square root, and you receive the quite important physical property of the flow. Is a very nice thing. So don't forget that this equation of state is always available, and you can use it always, no matter which is flow, isentropic or not isentropic, if it's subsonic or supersonic, compressible or incompressible. Basically, it's the universal equation, allowing you to get any thermodynamic property when two other properties are known. What else? Let's see which was the page 567. We did not calculate, for example, the characteristic properties yet. Let's do calculation of characteristic properties. You can do it using the equation, for example, 835. You can do it also using the relation 837, 836, and more. There are here 44, 45, 46. But for me, you know that I don't like to use in class such equations because it takes a lot of time to calculate. And instead of these relations, I always use appendix from the book. So we go back to the appendix and we will try to solve this problem using the appendix, not using the formulas. Okay, this is our appendix A, and here I will give you the following example. Let's see. I have first direct calculation. For example, my very small Mach number as for the nozzle calculation, for example, is Mach 1 is 0.1 and pressure 1 is 10. We always set quite high pressure when the flow velocity is small inside the nozzle, right? And I would like to know what are the Mach number and pressure in the characteristic point. Mach number is very simple, right? We know that characteristic Mach number is always equal 1. But the characteristic pressure is a question. We use the appendix to calculate. Here is the same strategy as we used before in the previous task. So we first get the stagnation property. I write that P0 is using the same formula as I wrote here, but in the opposite direction. It will be a product of pressure by the function of Mach number is P1, right, multiplied by, function of Mach number 1 from appendix A. And my P1 is 10, I remember. So I will see my Mach 0.1 here. And it's basically 1007. And I multiply by 10, so I receive 1007. We already had this, if you remember, in some of the previous examples, 1007 ATM. Don't forget about units. Don't forget that no matter which units of pressure you are using, you always receive a correct result. But in the calculation of temperature ratio, you need to use Kelvin always, right? And in the calculation of the equation of state, this one right here, you need to use always C units. Density in kilograms per meter cubic, the gas constant in joule per kilogram Kelvin, right, and temperature in Kelvin. So pressure will be received in Pascal. Don't forget about this conversion of units for the equation of state, because many people have errors calculating in wrong units. Okay, so I receive my stagnation pressure, and now I want to know what are the properties in the characteristic points of my P asterisk. What is the P asterisk? I will go again to see my isentropic flow properties in the appendix A. I will see my Mach 1, and the pressure ratio is here, so is 1:893. And the pressure will be equal to P0 divided by function of Mach characteristic from the appendix A. So it will be 1007 divided by 1:893. Okay, approximately 2 times smaller than stagnation pressure, as you remember. (532 ATM). That's the calculation. That's simple calculation. If you would like to know other flow properties, for example, what is the speed of sound or the velocity characteristic, we need also to set some flow parameter or thermodynamic parameter additionally inside the task. So not just Mach number and pressure, but also, for example, some value, temperature, for example, or density, to calculate temperature and to calculate speed of sound. Do not forget that just receiving two properties of the flow, of compressible flow, you can obtain as the result also two properties of the compressible flow. You cannot obtain more than two properties. And setting the three properties from the compressible flow, like one kinetic and two thermodynamic, you can obtain any quantities, any parameters you can have in the compressible flow. So that's the trick. Okay, this was the example calculation of the characteristic flow properties, and I would like to see what else can be given. Stagnation properties, you already, I hope, understood how to calculate, right? We had several calculations here of the stagnation point, and the static are just simple, that simple. I split in direct calculation. Flow is going in one direction. We define flow properties and calculate other flow properties, no matter before or after, and the reverse. and the reverse direction of the flow. And here is the trick. And the trick, if you assist this video, you will know that the trick is no matter which is the flow direction, the flow model is absolutely same, because the Prandtl-Meyer flow is isentropic. So no matter where goes the vector, the flow structure will be absolutely same for both cases. Okay, but for some people it makes a confusion, becomes a confusion when I draw vector in one direction and ask to calculate the flow properties, and then I draw the vector in the opposite direction and ask to calculate the flow properties, and people start to have problem because they don't know that it doesn't matter which is the flow direction. Since it's reversible, you can always put it in any forward or backward direction, no matter. Flow structure will be absolutely same, so do not forget this on your exam, and for your future also would be important. Let's start from point 6.1. We have flow properties at point 1 and the angle theta, and calculate flow properties at point 2, static or stagnation, and also angles μ1 and μ2. Is the Mach angle 1 and Mach angle 2. Here, for any kind of calculation for expansion waves, we use very simple relation of the Prandtl-Meyer flow, right, which is set in the Prandtl-Meyer function. Let's go to see the theory just a bit. Here is the Prandtl-Meyer function. Quite scary, right? So I will not ask you to calculate during the exam. This Prandtl-Meyer function is basically the angle as a function of Mach number, and also function of a gas constant, which is basically constant for most of our calculations. Sometimes it's changing for high temperature. We already discussed last time how to determine if it's constant or not. And here is we are talking about just Mach number. This function is tabulated also in the appendix of the book. It's appendix C from the book, and the solution between 2 points in Prandtl-Meyer function is given as this formula 943, that the rotation of the flow theta, or it's same as the angle of the body, because we know that the flow follows the direction of the body. So it's the same direction of the flow or direction of the body, is equal to the difference of two Prandtl-Meyer function. Prandtl-Meyer function at point 2, where flow was accelerated, minus Prandtl-Meyer function at point 1, where the flow had lower velocity. So higher velocity minus lower velocity. And since theta is given as the angle, right? So the Prandtl-Meyer function also is the angle by itself. The angle of μ1 and μ2 is also given in the formula 931, as you know, is depending on the Mach number. This Mach angle exists when flow is supersonic, and when flow has Mach 1, it's 90 degrees, and then with increase of Mach number in supersonic regime, this Mach angle decreases, as we know, and Mach angle does not exist in a subsonic regime, right? Because of various reasons. Basically, because physically we cannot have such a flow structure in subsonic regime, and we cannot have Prandtl-Meyer flow in subsonic regime, and also because this equation has no solution if Mach is less than 1, so it will be negative under square root, and you will not have a real solution of this equation. So mathematically not possible, and physically also not possible. So let's go to our appendix C. Here are the Prandtl-Meyer solutions which we use to solve any case of the Prandtl-Meyer flow. First of all, I will give you properties at point 1. Let's see, Mach 1, some supersonic 1.2. Okay, and I will see, for example, pressure 1, 2, ATM, and let's see, temperature 1. How much could it be? Let's have 500 Kelvin. So these are the flow properties, and I need to see the flow properties after at section 2. Also here I set my theta angle, 10 degrees, for example. Okay. Here the model, it does not say to us if will happen flow separation or will not happen flow separation. We assume that no flow separation happens because flow is isentropic. Using the Prandtl-Meyer function and appendix C from the book, we are receiving Mach 2. So the nu of Mach 2, Prandtl-Meyer function at Mach 2 will be found as, okay, let's see, is this 3.5, 3.6, okay, 3.6 plus 10 degrees, so it's 13.6 degrees. We find this 13.6 in the table. Where is it? More or less this, right? 13.6 in the table, 13.7, okay. Close. And the Mach number corresponding is 156. So I find that my Mach 2 is 156. Okay, this is my Mach number after. Also, I see that my mu angle is 39.87, so basically 40, or very close to 40. Mu2 is equal to 40, and mu1 I had to see from the initial value, right? It's this 56.4. I will write just 56 degrees. So I have configuration, geometry of my flow, mu1 and mu2. Mu1 is where changes in the supersonic flow starts to happen. Mu2, where changes of my supersonic flow finish to happen. Right, and after this mu2, flow is uniform again and goes according to the direction of the wall. Okay, Mach number at point 2 I have found, and now just pressure and temperature, they can be found in the same way as we did our previous calculations. I will just write you the formula, but probably just calculate the pressure, but temperature is the same absolutely algorithm. Let's see. So pressure 0, it's constant for Prandtl-Meyer flow and is calculated as pressure 1 multiplied by function of Mach number 1 from the appendix A is 2 multiplied 243. Okay, this is our stagnation pressure. 2 multiplied by 243, 486 ATM, and now just calculate pressure 2. Pressure 2 is the ratio between pressure 0 and the function of Mach number 2 from appendix A. So it's 486 divided, where is my Mach 156? Is right here, and the ratio is 407. Right? 407. Okay. 119 atm. So this is my pressure at section 2. Same thing we do for the temperature. If we are interested to calculate the temperature, we know initial temperature, temperature 1. By the similar formula, we find the stagnation temperature. T0 is T1 multiplied by function of Mach number 1 from appendix A, temperature ratio we find, and then we find the temperature 2, which is temperature 0 divided by function of Mach number 2 from appendix A in the same way. So it's absolutely a simple thing and can be done really, really fast if you know how to act. Okay, that's it. The direct calculation is that simple. You can calculate stagnation or static properties. Of course, in the task which I will give you on the test, will be not given so many parameters to solve. Will be just given one of the parameters to calculate and finish, just to know if you understand how to calculate or pressure or temperature or density. It's that simple. Okay, let's go to task 6.2. Task 6.2 is the reverse. You have flow properties at point 2, and you need you have also the angle of the body, and you need to calculate the properties at point 1, μ1, and μ2. It's absolutely same thing, but you need to just use a Prandtl-Meyer equation in the other direction. Okay. Going back to the Prandtl-Meyer relation, that theta is a difference here, we express Prandtl-Meyer function at point 1, and in this case is the difference, right? It will be, okay, a new m2 minus theta. Prandtl-Meyer function at point 1 is mu at m2 minus theta. Here we understand that the value should be positive, right? So the Prandtl-Meyer function for Mach 2 will be always bigger than the angle of the body. So we have such an example. Let's see. Appendix C. Okay. Let's find some big value of Mach number. For example, this 578. Mach number 2 is 178. Okay. And we are interested to have theta of 10 degrees again, and we would like to know which is Mach 1 in this case before. So just take the nu from here, right, is 20 degrees. Basically, I will make rounding, it's 20 degrees. So nu of m2 is 20 degrees. Mu of m2 is 34 degrees. Okay, and the difference nu of m1 is the difference calculated by this formula right here is 10 degrees, right? Okay, this was the formula for calculation. And we receive this value. I go to search my 10 degrees. It's right here, the closest value. This is the line. Now I understand that my Mach number is 144. So from here, my M1 is 144. My inclination of the Mach line is 44 degrees. A coincidence, right? 144 and 44 degrees, a coincidence. And that's it, basically. If you would like to receive some thermodynamic flow property, for example, pressure or temperature, you can also do this calculation in absolutely same way as we had in example 6.1. For example, P2 is 2 atm. I just repeat the formula, but I will not do the calculation because it's absolutely the same calculation. Is P0 P2 multiplied by function of Mach number 2, right? And pressure 1 is pressure 0 divided by function of Mach number 1 from Appendix A. Both are taken from Appendix A. And this is how you calculate pressure in section 1 or any other thermodynamic properties in section 1. Okay, the example 6.3. Example 6.3 is when you have the flow properties and you need to calculate theta, mu1 and mu2 is absolutely the same thing, right? We just need to rearrange things. Let's see. Mach 1, 1.2. Mach 2 is 2. So we are accelerating. We would like to accelerate from Mach 1.1 to Mach 2. We need to know which should be the body geometry and what will be the Mach angle mu1 and mu2 where flow changes start and the flow changes finish. This flow here. But as I told you already, equivalent to this picture right here. So mu1 and mu2 are important when you are designing all other bodies, when you are planning all the bodies. So these lines probably should finish or be inside some region, acceptable region. But okay, in this case, we are not talking about this question. It's already a very practical question. We just need to know the body geometry. That's very simple, right? We use directly calculation that theta is nu of m2 minus nu of m1. And for my Mach number 2 and Mach number 1, I just see it in the appendix. Mach 2 has 26.4. 26.4 minus at Mach 1 is 3.6. So the difference will be how much? 22 and 8 degrees. So having body of 22.8 degrees angle, we having Mach 1 1.2, have at the exit Mach 2. That's very, very simple and sometimes very useful calculation when you need to accelerate to some certain value of Mach number, or you need to decelerate from some certain supersonic Mach number to subsonic Mach number given, right? And you need to define the geometry. Very useful equation. So same thing you do if you need to calculate 0.6, 0.3, and you have, for example, thermodynamic and velocity properties. One example like this I can give you is, for example, the temperature 1 is given, temperature 2 is given, okay? And in this case, the velocity also must be given. Velocity 1 is given and velocity 2 is given. And you need from all these calculate which is the angle of the body allowing this transformation from section 1 to section 2 or vice versa. And in this case, what you do, I think you already understood. From these two parameters, you calculate Mach 1. From these two parameters, you calculate Mach 2. And applying directly to the formula of Prandtl-Meyer function, you calculate the theta angle of the body. That's That's simple. That's simple. Nothing of complicated. Calculate speed of sound, calculate Mach number, and calculate date. Just very simple operations, I hope. Okay, the point 6.4 is very similar to the previous points, just flow going in the reverse direction, but all the equations are the same. And here the flow properties will be given at point 2, where the Mach number is higher, and need to calculate the flow properties at point 1, where the Mach number is lower. And the calculation is absolutely similar, absolutely same. And I even do not see if such an example is necessary, because we already had today calculation from point 2 to point 1. It was these examples here, right? 6.2 is absolutely repeating example 6.2, but the vector is going just in the other direction, which does not change anything inside the calculation process. It's the same. Okay, that's are all tasks or examples of the tasks given for the oral test, and I think if you follow these recommendations, you can solve a lot of different cases, not just for the gas dynamics, but also for your practical future needs. And I think you already understood that gas dynamics is a quite powerful tool for any tasks of the flow and has a lot of analytical models. I'm not giving you anything of advanced or higher chapters of aerodynamics. From the Anderson, there are several useful models, for example, analytical models for the hypersonic flow estimation of some flow properties like pressure coefficient, for example, for compressible, transonic, and supersonic flow for airfoils. But I think the most important part is given already in these tasks which I gave to you and explained to you. If you are interested to solve other tasks just for your curiosity, please let me know if you need some help, and I will be always happy to assist your education until we have such a possibility.